So we just completed that example with limits, which was very visual and gave us a good sense of what a limit is and how we can calculate it when we have a graph. Now we move to some more algebraic and perhaps more rigorous techniques to evaluate limits that don't involve graphical approaches. First option to try and find out a limit is to use a table of values. This is very much a brute force approach where you're trying to do what we were doing visually, but with numbers rather than visuals or pictures. So we'll look at this limit here as x approaches 2. We know this is a two-sided limit because we don't see the little plus or minus on that a, so we know we're going to have to look at the values approaching 2 from both sides. And we've got a parabola function in here, or a quadratic function, x squared minus x plus 2 to work with. Okay? So we're going to use a table of values to try and see what's happening, what the behavior is, the function is as we approach this number in the middle, x equals 2. So we'll pick maybe 3 x values that are smaller than 2 and 3 x values that are bigger than 2. And we want these x values to approach 2 from either side. So from the left, we can start at 1.9 and go 1.99 and 1.999. That should give us our limit from the left, or at least an idea of what that limit might be. And then we'll do a similar thing on the right, where maybe we start at 2.1, we go 2.01, and we go 2.001. Okay? In the second row here, we'll put our y values. Okay? Now, right in the middle, we have our a value, which is our 2. This is the point where we don't actually care what the y value is. As we said before, with limits, we're interested in what the graph is approaching, not what actually happens there. So we can cross out that y value as not of interest to us. From here, it's just a case of substituting these x values into our function and calculating the y values. So for the first one, that would be 1.9 squared minus 1.9 plus 2. We're going to do all 6 values. Obviously, that would be tedious to do by hand, so this is a great place to bring in our calculator. So pulling up our TI-nspire, we could just calculate this first one as 1.9 squared minus 1.9 plus 2, and we could do that 6 times to get each of the 6 values we need for our table. However, we can automate this a little bit and speed it up by creating a function to do this, substituting in 4's each time. So if you're not familiar on the TI-nspire calculator, if you use a colon equals or this special define equals located right here next to the catalog and right on top of the templates button, so that's control templates, you can actually define a function and then interact with it just like you would on your paper. So I can compute the next one by defining this function f, it'll tell me done, and then I can just call it by substituting in the values I need. Okay? This will speed up and cut down the errors as I do the remaining 4 or 5 calculations. So I can do each one of these. I'm going to do them all and then write them out. These are my values for the limit approaching from the left. It's actually rounding them off for me even. There are more decimal places in here if I need them. I can go up and copy this down and see a little more accuracy if I need. So on my table, let me bring this up a little bit, we can see the limit from the left is 3.71, 3.97, 3.997. That's definitely suggesting the limit is approaching a nice clean integer of 4. But in order for the two-sided limit to exist, we need it to be the same from the other side. So we'll just go ahead and quickly do the 3 calculations to the other side. So f of 2.1, f of 2.01, and f of 2.001. We can fill those in our table, and it also confirms the behavior that the limit is approaching that integer value of 4. The difference is from the right, it's approaching 4 from above, whereas from the left, it's approaching 4 from below. This looks like pretty concrete evidence to me to say that we can make that educated guess. It is approaching 4. So using a table, we can say that this two-sided limit with good confidence is going to be 4. All right, now that was a lot of work for a function which doesn't really have that much interesting going on. So you might be asking yourself, well, what would this number in the middle have been? Couldn't we just have calculated that? And as long as we're not at one of these weird places with an open or a closed circle or discontinuity, the graph will behave nicely and just come together and approach the function value there. Well, that's actually true for the majority of functions that we look at. Okay? So we can just do a direct substitution for a lot of limit problems, and that should really be our first attempt on all limit problems we do. So what is direct substitution? It just says if f is either a polynomial or a rational function, which is quite a big family of functions that we study, as long as a is in the domain of f, meaning we're not at one of those vertical asymptotes for our rational function, all of our limits will just be equal to the function values. Okay? Let me put this bluntly. You can just substitute in the x value and calculate the limit that way if you're dealing with either a polynomial or a rational function. Okay? So this drastically simplifies how we can calculate limits, such as this one we just saw. Okay? We know that x squared minus x plus 2 is a quadratic. Quadratic is a polynomial. Therefore, we can calculate this limit by just substituting the 2 straight in. Easy math. We get it out as 4. No table needed. A lot of time saved. Now, a lot of limits we're going to see in the next section when we start looking at derivatives are going to fail that direct substitution approach. Okay? Mostly due to an issue of dividing by 0. Okay? So we'll need some algebra techniques at hand in order to get us around that problem of dividing by 0. Okay? We're just going to list those techniques here to get them back to the front of your mind, and if you need to go review them on YouTube somewhere else, you can definitely go do that. Okay? So we'll need techniques like factoring. We'll need techniques like common denominators. And we'll need techniques like conjugates and even just algebraic expansions. Okay? Meaning multiplying out maybe a binomial or a binomial theorem or something cubed. We'll need to know how to do algebraic expansions without making any errors. So let's look at some scenarios where that direct substitution is going to fail and how these algebra techniques can get us around the issue and still evaluate the limit. Okay? So this top example, we have the limit as x approaches 1 of x minus 1 over x squared minus 1. So if we try a direct substitution here, we have 1 minus 1 over 1 squared minus 1. Okay? This simplifies to 0 over 0. We know dividing by 0 is not a well-defined operation, so we can say that is undefined. So unfortunately, our direct substitution approach fails. Okay? All right, well, let's try and simplify this problem down with algebra. Okay? We'll keep the limit here until we substitute it in. So limit as x approaches 1. And then hopefully you recognize the denominator is the difference of 2 squares, so we can factor it as x plus 1, x minus 1. Now, these factors cancel most of the time. What do I mean by that? I mean those factors, the x minus 1 and the x plus 1, cancel for every x value except one value. The only time that these two functions, 1 over x plus 1 and x minus 1 over x squared minus 1, are not equal is when x equals 1. Okay? So these guys are equal if x does not equal 1. X equals 1 is the only place these two expressions are not equivalent. And why is that? Well, we just saw the first expression is undefined when x equals 1, but this second expression over here on the right, in green, that is perfectly well defined when x equals 1. So why are we allowed to cancel this? That's the big question here. We're allowed to cancel it because we're doing a limit. And as we saw previously, limits are not interested in what happens at that value, just as we get infinitely close. So as long as we're not at 1, these are equivalent. We know with limits, we're not actually at the value, so these are the same. Now, we have simplified our expression down. We can try again. In substituting in our value, the limit goes away. And in this case, we are able to evaluate this, which means the limit as x approaches 1 of this function is 1/2. Okay? So that is the value of the limit in that case from both sides using algebra. We'll do one slightly more complicated example here. We got limit as x approaches 0 of this algebraic mess. It's not really a rational function or a polynomial. It's kind of a mix of a radical, a quadratic on top, a quadratic underneath. Okay? But we'll still try our direct substitution approach. Okay? We'll substitute in 0, 0 squared plus 16 under a square root minus 4 all over 0 squared. Okay? Well, that's going to turn into 4 minus 4 over 0, which again is undefined. So unfortunately, our direct substitution fails, meaning we're going to need an algebra approach. The algebra approach here is a little more complicated. The algebra we need is a conjugate. So we're going to take this expression. That was a terrible square root. I definitely need to redraw that one. We're going to take this expression and multiply it by its conjugate. And how you would know to do that, it's really just practice. Okay? So you'll do enough of these problems where you start to see the patterns and you start to kind of get a feel for what will simplify and get those limits to work out for you. Okay? So the conjugate here is just the square root of x squared plus 16 plus 4 rather than minus 4. And what that conjugate is doing for us is it's creating a difference of 2 squares between these two parentheses on top. Okay? Now the whole goal here is to get this x squared in the denominator to cancel, because that's what's causing the division by 0. So the hope is that this algebraic step, while it looks like we're making the problem more complicated, and we are for a moment, it's eventually going to lead to a simpler problem where we'll be able to direct substitute. All right, strap in and get ready for algebra. If we FOIL out these two parentheses on top, square root times square root should give us x squared plus 16. You can do that algebra check yourself. Okay. We will then get plus 4 square roots. So 4 of these square roots, x squared plus 16. We'll get minus 4 of these square roots. You can probably see what's going to happen already. And then finally, we'll have a minus 16 on top. Now, we could multiply out the denominator, but I would encourage you not to. Remember, our whole goal is to get that x squared in the denominator to cancel. And if we multiply it in, it's going to be harder to cancel it later, and we're probably just going to end up factoring it back out. We're keeping the limit as x approaches 0 there until we substitute in. And beautifully, these square roots in the numerator cancel. The 16s in the numerator also cancel out. So we're left with x squared on top, and in the denominator, x squared times that parenthesis which came from our conjugate. Again, properties of algebra. Your algebra needs to be strong on these problems. These x squareds also cancel. Now don't forget, that leaves you a 1 on top. Okay? Now, what was giving us trouble when we were trying to evaluate this limit, it was this x squared in the denominator, and finally we've got that to cancel. So this seems like a good place to try and direct substitute again. So if we do that, the limit can go away, and we can see if our direct substitution is successful. A little bit of number crunching here. Our division by 0 issue has gone away, and we're able to calculate this limit as 1/8. Okay, let me move that up so you can see it. Now, the final problem we'll cover with limits is a unique scenario where sometimes you do some algebra and your problem does simplify, but that still doesn't help your direct substitution. So we'll look at this little problem right here. The limit as x approaches 1 of x plus 1 over x squared minus 1. This is very similar to the first problem we looked at on this page. Okay? We'll factor it again using a difference of squares. We'll have algebra that cancels. Okay? So we get one of these parentheses to cancel. It's the x plus 1. we're left with 1 over x minus 1. We try and substitute in, and we still end up with the same issue. We've got a 0 in the denominator, which still makes this undefined. So we tried to do algebra to simplify this, and it was unsuccessful. What does that mean? It likely means we've got a limit does not exist situation, or we've got something where the function is just always going to be undefined. Okay? Your best approach here when you can't get that algebra to simplify, okay, go back and use a table approach again like we did in option 1. Okay, so I'm not going to complete this example, but you would set up a table, put your 1 in the middle, pick some values that approach 1 from below, 0.9, 0.99, 0.999, and then pick some values which approach 1 from above, 1.1, 1.01, 1.001, and then try and see a pattern or a suggestion of what these values are approaching from either side on the left and the right. All right, this completes our lesson on limits, and we should now be prepared in the next class to go on to derivatives. I look forward to seeing you then, and please remember, if you want a copy of these notes, don't forget to like the video, hit subscribe, and drop your email down there in the comments.